covered particle stability. We talked about that electrical double layer effect, particles shielding each other, wanting to kind of push each other away. That was the reason we want to cancel out that charge. And we talked briefly about, okay, if we have a more dense charge, like a +3 or something, that's going to occupy a lot less space as an ion to satisfy a lot more charge. And that makes a very big impact that we can see in a few ways, basically shrinking that barrier. Okay, so we're just trying to reduce the force field that is ionic strength or ionic involvement with each other, so that we can let these van der Waals forces be like a magnet to attract them to each other. So what does that say about this actual process of them sticking together? And that's what I want to cover today is, okay, well, how do we then mathematically describe these particles colliding, sticking together, and make some sense of how fast that's going to happen so that we could design a system based on wanting them to stick together. So our flocculation then, I think I mentioned this already, but we're taking multiple particles and ultimately creating new individual particles that are made up of the components of the particles stuck together. So we had 3 particles here going into 1 that was made up of those 3. So what we want is gentle mixing. In fact, we want as much mixing as we can without pulling the particles back apart. So we're going to make some sort of assumption here that anytime we're talking about flocculation, we are not mixing so rigorously that they're breaking apart. Okay, that is possible, but we're just going to assume we've lowered it enough so that that doesn't happen. So we want mixing conditions so that we don't really have turbulence, but we have a lot of capability for the particles to collide together. And ultimately what this is going to do is allow us to reduce the number concentration of particles over time. So we will essentially have a decay reaction when looking at the number of the particles. We're not changing the volume, we're not changing the mass, we're not changing the particles aside from causing them to stick together. Okay, so the number then, if this was 3 particles per milliliter, this would be 1 particle per milliliter. We've reduced the number. Okay, so that's what we mean when we have a negative rate equation here. That also means we have larger particles. So whereas initially these were 1 millimeter, now we have 3 of those 1 millimeter particles have some new value here. Okay, so the question then becomes, if we've got this milky substance and we want to cause that flocculation as we see here so that we can do the sedimentation, well, how long is it going to take? How big of a reactor do we need? What is this rate constant going to look like? And that rate constant is going to be a function of a few things. This is going to be the mixing, something about the mixing intensity. The rate itself will depend on the number of particles there are there. And in some sense, the K itself will capture sort of the space occupied by particles. So we'll say space occupied, and we'll fill all of this in more elaborately and technically in a moment. So we've got how much mixing we've got going on, how much space the particles are occupying, and it'll also include something about how well we did at the coagulation, the destabilization. So how sticky are they now? How often are they going to, when they do meet each other, are they going to stick together? So we'll have some aspect of destabilization. So we have essentially equations to deal with K so that we can know something about K given the particles that we have. So that's kind of where we're heading. So the first one I want to talk about is mixing conditions. So if we imagine a scenario where we have the wall of a container or the paddle wheel of some stirring agent in our solution, then this is that surface here. We can compare the movement of water next to it, where we have a lot of drag forces. If we take a look at with distance away, we'll just say that's y is distance, away from that surface, if we look at how the velocity of the water next to it changes, that'll give us a gradient, which is our mixing intensity. So if we had a gradient that looks like this, where we have velocity of water here changing as a function of distance away from that surface, and eventually it'll probably peter out into the water's just moving at some velocity. But in that space near it, we can say something about the mixing intensity, because the force of drag is, of course, slowing down the water right next to the surface. And then further away, the water is moving relative to the surface, is moving faster. So based on that gradient, you can imagine if I'm slowly pushing a paddle through the water, that gradient's not going to be very sharp, right? It's going to be the water right next to it. Yeah, it's a little slower, but the whole thing is just moving so slowly, we don't expect much of a gradient. So the sharper the gradient, and I'm going to put the velocity term here. The sharper the gradient, the more intense the mixing. Because if you move it fast, there's going to be a big difference between the speed of the water right next to here. So that's all it's saying. We don't really need to know this too much. This slope then we could describe as dv dy. And the whole reason I'm just writing all this out is just to show you where the units are coming from and kind of why it makes sense that way. So that's conceptually, like if you're moving it fast, the difference between the water right next to the paddle, which has to be slow for drag, it's going to be a big difference from the water further away. So then the larger this number, the more intense the mixing, essentially. And the units for this gradient here, or this metric, this mixing intensity, G, they're going to be, if our velocity, let's say, is meters per second, and then distance we do by meters, that's going to come out to be seconds to the minus 1. Right? So our units for this mixing intensity is a 1/time unit. In fact, we'll keep it at seconds specifically for our equation here. And that tells us something that might match very well with the units that we would have for our first order rate constant per time. So just wanted to illustrate that, kind of give you a sense of where this mixing intensity value is coming from. This is G, and mathematically we can define it based on the power we're putting into stirring. So if we have maybe a big vat of water and you're trying to stir it by hand, you'll get tired out trying to get a high mixing intensity, right? Because it's going to take a lot of effort. You're putting a lot of power into it. Whereas we take a lot less to mix my bottle, right? So it's going to have some function of the power that you're putting into it, the volume of the basin, and the viscosity. Because if you tried to do that with honey, or you're churning butter, let's say, it's going to be a lot different than if you just have water or something that's less viscous. So those are the three things that go into it, and they're captured in this equation by the square root of power in watts, the dynamic viscosity of water. So we have kilograms, meters, and seconds. Watts are also in those units if you were to dig it apart. And then the volume of the chamber. There are several volumes around, especially if we go from like the flocculation and then think about the velocity for sedimentation, because there are two related topics here. So just keep these in mind that this is VB, that's the volume of the chamber, and that'll be in meters as well, cubic meters. So those are the parameters for our mixing intensity. This is an equation. You'll have it on your equation sheet. I recommend getting familiar with these as if you didn't have it on the equation sheet, so that you're familiar with what does the P mean and what does this V sub B mean. And the mu, of course, hopefully you'll know, is that dynamic viscosity. So just consider these. You'll have them on the equation sheet, but it might be worth treating them as if you're not, just so you know what pieces go where, and what that means, right? That's probably the bigger challenge, is what are the meanings of each of these. To remind you, let's say if you had kilowatts, you're going to have to translate that to watts, because we need the units to work out properly. Okay, so then let's talk about what is happening with our rate itself and talk about how we're going to build the rate equation now that we have some conception of, okay, well, the mixing, that's going into the K. There's a couple other things that are going to go into K, but I want to give you the picture of what's happening first. So, and I already mentioned this once, but let's imagine we have some volume of water here. And I'm going to put, let's say, 10 little particles in there. And through our flocculation process, we're going to end up with, let's say, just 2 particles, each containing 5 of those initial ones. And those are now, let's say, discrete particles that are sticking together. So we started with 10 per some volume, and now we have 2 per some volume, right? So this would be just like saying we have some n initial, so n naught. That's 10 particles per volume here. And now we have some n final is 2 particles per volume. Okay, so that's just a conception of when we change the number of particles, this is what's happening. We're changing it by compacting them into these aggregates. What's then interesting is we can say, well, as n decreases, the size of the particle is increasing correspondingly. And that's really what we want. If we remember back to our velocity of sedimentation equation, that was g rho particle minus rho water times diameter of the particle squared, 18 mu. And that diameter of the particle squared, that size of the particle is really important because that's squared. So that has a really big impact on how fast we're going to sediment these particles. So as we increase the size, that's why we're doing it, right? So that's going to be the driver in terms of our motivation to do this. And then we can see here the rate equation itself written as dn dt equal to negative kn. So we're going to continue developing k here, but we can use this rate equation to describe flocculation and put that in different mass balances, right? So if we had a batch reactor, we could do that as v dn dt equals negative kn in that volume. That would be a batch reactor equation, or a CSTR if it was pretty simple, let's say at steady state. That would be 0 equals q n naught minus qn minus vkn. We could derive from there, and we've done specifically that already in class, and we know that we can get n equals n naught over 1 plus theta k. That I'm just doing that by memory. You could divide everything by q. That'll give you the theta here, and these q's will drop out, and then rearrange and solve for n. You get that, right? We've done that, so we'll come back and derive something in a couple minutes. But what's interesting and perhaps more important for us is like that would give us the concentration of n, right? That would give us the final number of particles in our solution. That might be helpful, but what's really actually more helpful usually is to be able to compare the initial to the final in terms of how many of the initial particles are in each final aggregate. That way we can make some size comparison. So normally when we're working with these particular systems, whereas previously it might make sense to look for n or maybe n over n naught, I'm actually going to say n naught over n might be more interesting, because this is saying the number of initial particles in each aggregate. Technically that's per volume, right? Per volume. And then we have on the bottom number of aggregates, I'm just going to call them. also per volume, so that's just going to cancel, right? We can kind of just ignore the per volume. So what that means physically or practically is if we had this case here, we went from 10 per volume to 2 per volume, then that means n naught over n is equal to 5, which means we have 5 initial particles in every aggregate. And for me to say it like that as in a sentence form is actually pretty important because we'll see that in problems, and it's a good conceptual way to compare our systems. Because then we can know something about the size of the final particles, right? So it's just going to be the same mass balance process. We're just rearranging it to achieve a slightly different answer. So this, I'm going to write this out down here and say, for this example case, we have 5 initial particles in each aggregate. Does that make sense? Okay, make sure you are able to apply that concept to these problems, because that is oftentimes the sticking point that students mess up on conceptually and therefore don't know where to go with the problem. So pretty simple when I say it like that, but just spend a little bit of time to make sure that that process, the way to describe it in a sentence to the math, makes sense. And that'll be helpful. Okay, so that kind of brings us back to, okay, well, what about K? How do we know K? If we look at our equation here, you know, we could rearrange this one if we divide both sides by n naught. Or excuse me, divide both sides by n. We could get n naught over n equals 1 plus theta k. So we know something about theta. We probably are given something about our initial particles. Then we can find something about the final if we know something about k. Right? We probably have reactor conditions that tells us theta. So brings us back to k. We know the mixing intensity is going in there. We know some other stuff is going in there. So what else goes into it? Well, here's our equation. We have k is equal to, we see the g here. So we know that part. But it's also has this, the alpha here, this is collision efficiency. I mentioned earlier that it will depend a bit on how likely they are to stick together. So how effective our coagulation was. This alpha gives us that. And this alpha, it specifically is referring to the fraction of collisions that occur that form a new larger particle. So what percentage of the time do they collide and make a new one? So if this is 1 as a fraction or 100% as a percentage, then we say that's the case when we have complete particle destabilization. So when we were talking about destabilizing our particles last time with the coagulation, if it all works well, we get 100% destabilization. That means every time the particles meet, they'll just stick together. Okay? There's some random chance involved with how often they're going to meet. That's where the G, and we'll see in a moment this omega term comes in. But this one, this is just a ratio. It goes from 0 to 1. It's unitless. It's just a fraction. What portion of the time do the collisions achieve a new particle? So it can be 0.5. It can be 0, which would mean the whole rate goes to 0 because they never stick together. That's the whole purpose of adding a coagulant in the first place, is to improve that from 0 closer to 1. So yeah, if we have aggregation, it's never going to be equal to 0, but you could say 0 is the perfectly stable particles, right? All right, so that's just that factor there. Then we have a flock volume, and I call it a volume, and then I say it's unitless, which kind of doesn't make sense if you think about it at first. This term is going to describe the volume in a given liter or cubic meter that is occupied by the particles themselves. So if I have some particles in my liter here, some of the space is going to be occupied by particles. And now if I had really dirty water, you can imagine that a decent amount of the water here, the volume, is particle matter, but it's still going to be pretty small. So what we expect from this is it's unitless because it's a volume over volume term. So it's volume of the particles, so the volume occupied by particles divided by really the total volume. Let me just do this. So that's what makes it unitless, assuming, and we have to do this, we get the units to match, right? So if it's cubic meters of reactor space divided by, or excuse me, like milliliters of particles or whatever, divided by cubic meters of reactor space, that's not going to work. We have to have the same units. So say this must become unitless in order for the math to work. So it's a good check for when you're solving these problems to make sure you have a reasonable number. First of all, the particles are always going to be a fraction that is less than 1, right? The total volume, you cannot have more than the total volume of particles in here, right? You could maybe have all of the water is actually particles, I guess. That would never make sense, but you can never have more than 1, right? So this flock volume is going to be unitless, always less than 1. And in fact, it's usually going to be a small fraction, right? And if you think about it, even if I have really, really murky water, if I got them all to settle, it's just going to be a sludge at the bottom. Most of the volume will still be water, right? So even considering very dirty water, this is usually pretty small. So something like 10 to the minus 5 or 4 or something like that. So if you get 10 to the minus 20, you're like, maybe that's a little small. If you get like 0.1, 10% of your volume is all particles, that might be a little much, right? It's still within possibility, I suppose, but most of our problems with drinking water probably not going to be so much of it. Okay, so then how do we define it? Well, it's actually pretty simple when we think about it in terms of what exactly we're talking about. So what we're talking about is, again, the amount of volume occupied by these particles per volume of water. So we can take the volume of one particle and multiply that by the number of particles in solution per volume that we're interested in. So if it's a liter, we would do per liter. So really, all we're saying here is the volume of one particle, assuming it's spherical, is going to be pi times the diameter of that particle cubed divided by 6. That's the equation for a sphere. And then we can multiply that by the initial number concentration of particles, because that is exactly what we have here, right? So that flocked volume term, we'll see these volumes cancel, right? The volume term on the top will cancel with the volume term on the bottom, and we're left with just some number. And so that fraction is just the fraction that are there, right? So in that manner, we get this to be essentially unitless as a very small fraction. Does that make sense? Okay, so then the only tricky part here is you're probably going to be given particle units, diameter in, I don't know, millimeters, micrometers, something like that. So then you need to convert that to cubic meters, and then you need to convert whatever denominator for your concentration to the same cubic meters, or whatever you decide you could use, but you just have to make them match, right? So that'll be the predominant challenge is correctly matching your units for flock volume. Okay, so then to get K, we have two different equations we need to deal with, the G and the omega, and we need to know something about how destabilized they are. So that'll usually be an assumption. A lot of times we'll say completely destabilized. So you know that's 1, right? So that's our equation. That's the status. I guess I have this repeated, sorry. I think the only thing I added here was, which I meant to take out the previous slide. That's just defining these two here. So nothing else new there. Okay, so let's take on a problem, and I'll help you through this to an extent, and give you some time to think about how you would approach it. What I'll probably do is give you a few minutes to, after kind of walking through the setup with you, I'll probably give you a few minutes to think about the next few steps, how you would approach that, and then move you along a little bit and give you a little more time to think about, okay, well, how would you finish the problem from that point? So that's my plan. So we have a follow-up from the example we did last time, where we had 0.01 millimeter silt particles and the sedimentation basin was not able to remove all of them. So we're going to destabilize them. So this says to improve their settling, those same silt particles from that example are completely destabilized. So that's already giving us some information there. All right, so that's, find my cursor again. So that's telling us that alpha is equal to 1, right? That collision efficiency. That was by adding alum, and it's passed through one of two side-by-side, well-mixed flocculation chambers. So it said passed through, so this is going to be a continuous flow. We have two side-by-side chambers. So I'm going to go ahead and draw that. These are both flocculation chambers, so we have some sort of mixing happening in here. And the chambers are cubic, so that makes the volume calculation pretty easy. Each of their dimensions is 3.5 meters, so 3.5 meters. We are given something about the power input. So it says they are mixed with paddle mixers that input 2.5 kilowatts of power into the water of each chamber. So given power is 2.5 kilowatts. The water entering the flocculation chamber contains 10 to the 5 particles per milliliter. So we have some N naught entering. By the way, we have Q here for the total coming in, and it's split equally to both, so we know that we can do half of that in each chamber as our Q. Okay, so then we are also given this value for N naught. So N naught is 10 to the 5 particles per milliliter. And the question is, what is the average diameter of aggregates leaving the chamber? Okay, so there's like a lot to do before you get there, because we're going to need a mass balance and all of that. So I'm just going to write down the relevant equations for you and give you a few minutes to think about how you would put this together, what kind of a mass balance you would do, and see how far you can get with that. And I'll come back and then take a few steps with you. One thing I meant to mention earlier, G is in per seconds, and if you look at K here, the that alpha, the collision efficiency, is unitless, the 4 is unitless, pi is unitless, and the omega is also unitless. So the only units there are coming from that mixing intensity. So it works out that is a first order reaction rate constant. Okay, so take a few minutes and work towards the answer and consider how you would assemble a mass balance with this system. All right, so I'm going to take the first couple steps here, see if I can get you guys, get us all on the same page. So with the drawing we had, I want to start there and elaborate a little bit. We can essentially just take one of them and do a mass balance on one. And because they're identical, we know what's going to happen to both, right? So what I'm going to do is I'm going to say Q is actually 1.5 mgd for a system where we have a typical CSTR. We have complete mixing, we have an input and an output, and the concentration doesn't change if we split the lines, right? That's just the same stuff is coming in, and so it doesn't really matter the N over N naught, the N naught over N, whatever. That's going to be the same for both reactors. We have the same reaction, same dimensions, all of that is the same. So I'm just going to take this system and do a mass balance for this one to understand how big my particles are going to be at the end. And in order to get some information about how big they're going to be at the end, I'm going to look for an equation for N naught over N. Like I said a few minutes ago, that's kind of a good target. So I'll go ahead and write it up then. We have Q, well, first of all, should be at steady state. There's no real reason it wouldn't be. This is a reactor. It's been running. We weren't given any information about time or anything like that, or accumulation or whatever. So I'm going to go ahead and assume it's steady state. Then we can say Q N naught minus Q N minus our reaction, because it's a decay term, VKN, is equal to 0. Right, so that's our steady state equation. We'll go ahead and divide everything by 0, or excuse me, by Q, and say 0 is equal to N naught minus N minus theta K N. And here, I'm going to divide everything by N, because I think that'll simplify in a way that's getting us closer to our desired result. So 0 equals N naught over N minus 1 minus theta K. So we can just add this guy to both sides, and then we'll get N naught over N equal to 1 plus theta K. Just like we said a few minutes ago. So that's our equation then to understand how many initial particles are going to be in each final one. Okay, so that's why I said and was stressing that it's good to know your target like that to have some comparison. Technically, you could say N over N naught, which would be how many final particles are there per initial one, and then that would be 1 over. That would be like a fraction. There's 0.2 particle aggregates for every 1 particle. You could do it that way, but you'd have to flip it. It's just easier mentally if you do it this way. So that leaves us with a couple things. First of all, what's theta in order to solve this? And then more complicated, what is K? So we'll start with theta. That's V over Q. So if we take our system here, that's going to be 3.5 meters on every dimension, and we need to cube that. And we'll divide that by our Q, which was 1.5 mgd. We have some conversion factor there, so that's going to be like 1.5 mgd times that 0.0438 cubic meters per second. That volume, I'm just going to go ahead and write it here. Volume of the basin, if you cube 3.5, I think it's what, 42, it's 875. Is that right? Just remembering from the other sheet. Okay. So that's our volume. And then our theta comes out to be then what? Does anybody have that for me?
6 seconds.
652? Okay. Sorry. Yeah. Did not mean to do that. Okay. Sorry about that. Just flipping through with my old slides, and that was not a good plan. Okay. All right, you said 652 seconds. Okay, is that right? All right, good. So we've got that, and then if we do, so we've got that for our theta. Then we need k. We said k was going to be that alpha times 4, omega times g over pi. So we need g. G was going to be that square root of the power over mu times the volume of the basin. And that power needs to be in watts. So you needed to convert from kilowatts to watts. So that would be, power would be 2,500 watts. So if you do that, I think it's what, 225s per second? Yes. So right, thank you. Second to the minus 1. Okay, so we have part of that. Then we need the flock volume. And that guy was going to be essentially that pi times diameter of the particle cubed over 6 times n naught. So that's going to be pi times that dp, which was 10 to the minus 5th meters. If we convert it to meters, we have to cube that. And then we multiply that by that initial number, which was 10 to the 5th particles per milliliter. So to convert from milliliters to cubic meters, we have to multiply that guy by 1,000,000, because it's 1,000 from milliliters to meters, or to liters, and then 1,000 from a liter to a cubic meter. Right? So that's, well, essentially, have 10 to the minus 5th cubed. So we're at this point, 10 to the minus 15th. Then we have that multiplied by 10 to the 5th. So that brings us down to 10 to the 10th. And then also by 1,000,000, which brings us down somewhere, if I did that right in my mind, which I don't know if I did, it'll bring us closer to 10 to the minus 3 or 4, somewhere in that range. Maybe 5. So I probably did that. Anyway, anybody have that number? If you did that conversion? I have it on my other slides, but you've got it. So what I have is 5.24 times 10 to the minus 5th. Does that make some sense? Anybody get that? Yes. Yeah, okay. Is there an issue? Have some problems? Okay. Okay, so that's then our omega. Now we can finally get our k. And that's going to be 1 times 4 times that 5.24 times 10 to the minus 5th times that mixing intensity, 225 seconds to the minus 1. All of that divided by pi. I think, anybody have that number for me? Should be 0.015.
Yeah.
Seconds to the minus 1. Okay, so with that, got all that information together now, then we can say n naught over n is equal to 1 plus that theta, which we calculated, 652 seconds, times the k, 0.015 seconds to the minus 1. If we did all that properly together, just based on my memory, this should be, what, 10.8? 10.82 or something? Is that right?
Yeah, I got 11.02.
11.02? Anybody else have a... It's approximately 11, and depending on how we round it.
Yeah, just use it.
I'm going to use what I have in my previous thing, and maybe I did something wrong at some point. It's about that, and I'm only going to use this from my other work just because we'll just assume that math works out, because then I know the final answer to give you so that I'm not doing it wrong. If you see an error here, or like what I did wrong, let me know. I could even just show you what I've got over the other side. But. Okay. So with that, I want to give you just a couple minutes to think about how you would get the final aggregate volume, or excuse me, diameter from that point. Okay. So we did the mass balance. How would we finish?
Multiply n over n naught over n by the initial volume of the complex.
But we need so that'll get us the ratio of the, like you're on the right track, because that'll give you the ratio of the volumes. But then you need to convert to diameter, right? Because the question's asking for the average diameter. And by the way, probably the trick here is to recognize that since we're going to be assessing this in a sedimentation context, we're going to make a new assumption that the final aggregates are spherical particles. It's kind of a weird assumption to make, but that's what we're going to assume. That can give you the way forward to make that comparison. All right, so some of you seen the relationship I said here. We know that if each particle, each of the aggregates has 10.82 of the initial particles on average, then we can say 10.82 times the volume of the initial particle is going to be the volume of the aggregate, because we're conserving volume here when we merge them together. Then magically it becomes a sphere again, and so we can then say 10.82 times the volume of a sphere for the one particle is going to be equal to the volume of a sphere for the final particle. Okay, so at the end of the day, we can make a relationship where we're going to cancel the 6's, multiply both sides by 6, divide both sides by pi, and we're left with 10.82 times the diameter of the particle, initial particle cubed, is equal to the diameter of the aggregate cubed. And then from there, we can say this diameter of the aggregate is, I think it was 0.022 millimeters as the final answer. Okay, does that make some sense? All right. Any questions, issues? It was kind of an awkward problem in a sense that it asked you a pretty straightforward question, but there was a lot to go from the starting point through to the end, right? So if I were to give you a problem like this on an exam, I would probably break it into a few parts. And so what you would see then is A, maybe draw the diagram, describe the mass balance, something like that. B, what is the value for K or something. So I'll probably give you problems on this scale, but my aim is to break them apart so that I can test how you're able to apply your knowledge for the different pieces, and also hopefully kind of steer you a little bit with the problem. Okay, so one thing I wanted to highlight before we finish there is this is kind of an interesting case where we saw two reactors in parallel. So we had this arrangement over here where we had two reactors and we selected one. And I wanted to bring back a short discussion on what would happen if we had two in sequence, so in series. So what would happen if instead we had two reactors, one here going into the next one here, and water flowing through like that. So how would we know the dn, or let's say the n over n naught for the final? And I meant to include one more blank slide so I could draw this out. I have a previous session slide we can take a look at, but I guess I'll just do it that way. From a previous notes, I was deriving this stuff. So that was from the former problem. So my question to you is, if we had a reactor like this, and maybe even more, if this is the initial, and then we say N1 here, and N2 here, the question is, without looking ahead down below, how do we know something about the initial over the final? Now that I've drawn your attention to the stuff on the bottom, I'm sure you can't help but to look. But if you're to think about that, you know, what would that mean, let's say, for a plug flow reactor versus a CSTR? How would you write that? And the answer, I'm just going to talk it through. The answer is, well, you can take something that you know, which would be, N1 over N naught. Excuse me, let me just rewrite this because I think it'll be a little clearer. I'm going to do the final, right? The final over the initial. That's usually what we look at. Obviously today we kind of invert it. You could invert this too, but for the moment I'm just going to leave it as N2 over N naught. We know that we do have N1 over N naught very pretty confidently. We've done that several times for, depending on what kind of reaction's happening. And we can multiply that by what's happening in that second reactor, which can be described as N2 over N1. So rather than try to make sense of all of them together, we can break it apart into pieces. So we're going to do this reactor, relate that to this other reactor, and then if we notice, here the N1s will cancel, and we'll be left with N2 over N0. By just simply multiplying the two mass balance equations together, so mass balance for this one and a mass balance for this one, because they're connected by that N1 in between, that'll actually simplify the problem. And so if, let's say, we are using a first order, let's say a first order decay as an example, we know that N, let's say a generic N over N naught, is going to be equal to 1 over 1 plus theta k, right? We talked about that before. That's our derivation if we're solving for the fraction remaining of N, right? So we could put that in here and say that's going to be equal to, and let's just say we have a theta 1 here and a theta 2. So we could say that's equal to 1 over 1 plus theta 1. Yeah, fix that. Theta 1 times k. That stuff multiplied by 1 over 1 plus theta 2 times k. So that would be our equation there. Now, if theta 1, if these reactors are the same, theta 1 is equal to theta 2, then this is equal to 1 over just simply 1 plus theta k squared. Okay, so you can see how we can pretty easily end up with, n reactors. And so let's say n is 5. So we could have 1 over 1 plus theta k to the 5th power, right? Just based on how many identical reactors we have lined up in series. In fact, this is actually, if we think about it, a plug flow reactor could also be modeled. I know I told you guys the conveyor belt thing, but we could also model it as an infinite number of tiny little CSTRs where water's coming in, mixing in that little spot, and then moving to the next one. And so it turns out that with whatever algebra, calculus stuff you want to use to convert this to an infinite, the math ends up the same. I think it might be a Taylor expansion or something. Math becomes the same as what we normally have for plug flow. So the other way to derive that is to just have an infinite number of really tiny CSTRs. Just kind of a side note there. So backing up just a little bit, if we do n naught over n1, that's this case that I had derived before, where we had a flocculation example, and instead of the 1 over, because we flipped it, we were looking at n1 over n naught, or let's say in this case n3 over n naught. Then we could say that's 1 plus theta k, and ultimately then we could say 1 plus theta k, if they're all the same, cubed, right? Because it's the same exact process, we're just looking at it flipped. Now, that's different than what we did today with this problem. And so in here, we knew that n naught is the same in both cases, and we just divide the flow according to what the problem said. It was split equally, so we just divided equally, and then we had those volumes. So you can then think about, you could potentially solve a case where you had different reactor volumes here. You would just have to do the same problem twice for the two different reactors, right? So then you'd come up with probably an N2 in this case would be different than N1, but the same process is applying. So I just wanted to point that out. Last thing I'll note here is for plug flow reactors, usually they're a little bit like a hose pipe. And if you think about it, if you add one plug flow reactor and let's say you go to another one, by adding a second one, essentially you're just lengthening it. So assuming your same reaction is happening in it, you're just giving it more hydraulic resonance time. So this is an even simpler case. If you have a series of plug flow reactors, it's just like having a longer tube, right? The reaction can go for a longer time because it has more resonance time. So that one's even simpler, but the math, you can still take the same math approach, right? Because in that case, it would be, let's just say n over n naught is equal to e to the minus kt, but really we put theta there. And then, oops. So then if we have that times another, let's say theta 1 times e to the minus k theta 2, it turns out that the math of the logarithms is we just add those thetas together, essentially. It's the k thetas, those terms will add together, and we'll just be left with a larger theta. So that's kind of how it works out. With a plug flow reactor, it's much simpler, but you can use the same tools in either case. Okay, so I wanted to use that chance to introduce a slight bit more complexity to our mass balances, but it's actually not changing the mass balances themselves. It's just thinking a little deeper about how we can arrange them if we have a more complicated system with more reactors in place. And also to learn about flocculation and kind of practice that some. All right, any questions, comments? All right, so we will have the homeworks due on Thursday. We'll probably go over them then. I'll take a look at our schedule and see how we are tracking in terms of material to cover. If we don't go over them on Thursday together, what I will do is go over them with you on our exam review day in a couple weeks. Okay, so with that, I'll see you on Thursday.